Welcome back. We're going to begin our discussion on a brand new topic called chemical kinetics. Now, the knowledge you have obtained probably for the most part over the last 8 months would come in handy because it's really the time where we're finally wrapping up everything, and it'll be a great place for you to apply every bit of knowledge you have learned. And chemical kinetics is one of those topics. Okay, pretty much everything you have learned, you will see it applied here, and which is why it appears so much later in the coursework. Okay, so first let's define what is kinetics. Okay, first, kinetics has to do with rate, and whether you're coming from a physics perspective or a chemistry perspective or a biochemistry perspective, the concept is same. When you're measuring in a chemistry perspective, you have the word concentration, but the idea is essentially the same. Measuring concentration of species over a period of time or as a function of time. When I say species, what I'm referring to as reactants and products. Okay, that's essentially what I'm referring to. Okay, you will see I'll give more explanation on what I'm really referring to there in just a second. But when you're measuring concentration of reactants or products as a function of time, then we are dealing with chemical kinetics. Okay, so for the purpose, I chose this reaction, and we'll try to keep the same reaction throughout the course. Unless I have to change, then I'll probably change. Okay, so generally speaking, okay, this is our reactants. This is what we started with. Whether it's a single-headed arrow or double-headed arrow, it doesn't matter. It's what you probably started with. This is probably what you ended up with, which then started to produce more reactants. But fact of matter is, it's generally universal to call these reactants and these products. Okay, what are we referring to by saying concentration of species as a function of time? Well, there are certain ways to write a chemical expressions. Okay, and delta usually refers to change in something. Okay, so we are referring to delta concentration, change in concentration of N2 as a function of time equals to change in concentration of H2 as a function of time equals to change in concentration of NH3 as a function of time. The delta top refers to change in concentration. The delta bottom with T refers to change in time. So essentially what I'm saying here is change in concentration over change in time. This is what a rate really refers to. Okay? So, but if you keep in mind, in any reaction, reactants have to be lost for products to be made. So typically these will have a negative sign. Anything that's reactant will have a negative sign. Anything positive, any products, you can put a positive sign or don't put anything. They both mean the same. But here's what I'm telling you is, I will probably never give you a reaction that's balanced. In this case, I gave you one because I can explain the concept. How do we account for the ones and the twos and the threes? Well, this is one, so you don't need to do nothing about it. Hydrogen has a 3, so essentially you write it as 1/3 times this. Why do we write 1/3? Because it's lost at a rate of 3 times as faster versus this. So you have to always write it as whatever the number is, write it as 1/that. Okay, I gave the explanation. That's not enough. We can talk about it later at another point of time. Similarly, this would be 1/2 times this. Okay. This is how you write expression. Let's just do one more for the kick of it. Okay, H2 plus Cl2 going to HCl. It's all gas. Not that that's matter so much in this case. Okay, So if you balance this equation, this will be 2HCl. So if you have to write the rate expressions for this, or change of rate expressions for this, it'll be negative delta H2 over delta T equals negative delta Cl2, because they both have 1, 1, so you don't need to do anything. Say nothing, do nothing. Here it's 1 over 2. You can write the positive or not, it doesn't matter, but you can write, say. That's not adding, okay? That's just the symbol. So this is how you write content rate of individual species, okay? This is how you write rate of individual species, okay? Now let's do a math problem associated with this, because yeah, everybody can do this if this is on a test, but what they cannot do is what's about to come, okay? As I said, generally speaking, if concentration goes down, a negative sign is assigned, which is what usually we do with reactants. If concentration goes up means you're producing more. Concentration goes down means you're losing something. So positive sign is associated with products. Negative sign is typically associated with reactants. All right, so this question I stole from somebody. I don't know who, somebody, so many thanks to that person. So what it's given is, basically for the first part of the question, they want you to write the rate of disappearance and rate of appearance equations, just like we did in the previous case. So 2O3, this is decomposition of ozone into oxygen. They're both gases. Okay. Question A asks you to write the rate of appearance and disappearance equations. So basically that will be negative, right? This is already balanced for you. So it's 1 over 2 delta O3 over delta T. Okay. You can write a generally even bigger bracket if you want. That's how I like it, especially when I have too many things going on. I try to put brackets within the rest. And this is product, so it's plus 1 over 3. You know, within bracket, you write delta O2 over delta T. That's what you mean by this is rate of disappearance, right? Because that's reactants. And this is rate of appearance. Okay. Very good. Now, the second part is asking is, if the rate at which O2 appears, delta O2 over delta T equals 6.0 10 to the negative 5, it's asking for what is the rate of disappearance of this, right? This is very, very simple, okay? Basically, this, whatever's within the bracket is given to you, okay? So 1 over 3, okay, times this value is given to you, okay? That's why I had you write it this way. So it's easy. All you do is plug this in. What we need is this. Let's call it just X, okay? Makes life so much simple. How do we find X? Well, it's basically 2 times 3 over 6.0 10 to the negative 5. Also move the negative. All I did is multiply both sides by 2. Okay, so this gets canceled out, but the negative still remains. So basically, you can do the math. Let me get my calculator. So that will be all right. So 6 exponent negative 5. Okay, let me do the math here. Okay, I'm having trouble with my calculator here. 6 exponent -5. Sorry. 6 exponent -5 times 2 divided by 3. All right, sorry for that delay. I had some calculator issues. So it'll be -4 exponent -5. This was the answer I got. And that's what this is. See, if you set it up this way, no matter how lengthy this equation is, this is very, very easy, okay? And I don't want to extend this video by doing another problem because, you just have to know how to apply things into newer situations. And, all you got to do is do this. From there, everything falls in place. I mean, look at this. I mean, if this is a difficult problem, I would be keep going for another 2 or 3 pages, but this is all we have. Okay. So this is introduction to chemical kinetics on how rate of appearance and disappearance works. So essentially what I have shown you is very much the very, very foundational meaty portion of chemical kinetics. Okay, and I got, I think, 2 or 3 more videos to wrap this topic up completely. So stay tuned for additional videos on the topic of kinetics.